Thanks everyone that's still staying here with us. I will try to be short. I only have 15 slides. There's a end-of-light tunnel of today. So my name is Shen. I'm assistant professor from Utrecht University. I work in an institute called Copernicus Institute, which is a multidisciplinary institute. We deal with a lot of issues about sustainability transition. So I come from a division called Energy and Resources, where most engineers are located, and we also have ecologists, we have governance, social scientists, and we also have innovation science, which is somewhere between beta and social science. So my background, Laurie asked me to give a talk about 10 years experience. Feels like really, really old. So I was thinking, start to refresh on my own research line. I could summarize in 3 bullets. So when I started as a PhD student in Utrecht, the top one, the first one, triggered my interest and curiosity to continue to find out the answer. So do bio-based materials offer environmental benefits, and how? Are there trade-offs? The question there is, we know we can make bio-based plastics, we can make it biodegradable, then what? Are we done? We're then good or not? I'm moving away from that a little bit. Recently, I work a lot on ex-ante, so perspective LCA, because in this field, there are a lot of innovation going on. So new technology has been developed, new process has been designed. What I've seen, also we have observed in the, let's say, the fossil fuel industry, the petrochemical industry, is they had a lot of lessons for us to learn. We know BPAs, bisphenol A, is one chemical compound that you absolutely don't want in a packaging, food packaging, especially for kids. So now the legislation said, look, let's ban it because it damages our human health, it disrupts our reproductive system. Absolutely not. But why? The question is, I ask, why is BPA in the first place ended up in the bottle at all? Why should it be there at a commercial scale, larger scale? So what can we learn for the new innovation, in the bio-based innovation? Can we prevent this happen? The same story goes with microbeads. So there are many countries banning microbeads because wastewater system is difficult to filter them out. It ends basically everywhere as microplastics. The same question could be asked, why at all it has to be in the market in the first place? It shouldn't happen, right? If we do proper responsible innovation. The same, I want to apply that concept for bio-based economy, for bio-based innovation. So that was my second research line. Continuing that is, recently I developed a strong interest trying to find out environmental impact of macro, micro, and the nanoplastics. It's a lot to discover. The problem is sometimes beyond my imagination if I look at the literature. So today, I will only focus on the first one. So if you are interested in the other 2, we can have a talk afterwards. So as Laurie said, I was among the first, so I was thinking yesterday very hard. When did I start? I started as a student assistant in a project of BREW. BREW was done some 15 years ago. It was among one of the first study where the scientists are trying to answer the question by analyzing 20 bulk basic chemicals that can be produced by so-called white biotechnology, which is another word to say fermentation. So there at BREW, we did a lot of conceptual design because nothing exists on large scale some 15 years ago. So there was a lot of interaction with industry, a lot of literature reading. So the ex-ante techno-economic and environmental analysis was carried out. And we only focus on cradle-to-factory gate on these something like 20 bulk chemicals. of course, today, if I have to do the study again, I would choose totally different scope. But that was 15 years ago. What we found out at that time, there was a clear opportunity for NRU represent non-renewable energy use. So that's a summation of fossil fuel and the nuclear energy and the greenhouse gas reduction for these 20 basic bulk chemicals which can be made from bio-based route. Under the favorable condition, such as very high oil price, some bio-based monomer could take up very, very fast. And that was actually evident. Let's say a couple of years ago, we saw a large investment for bio-based ethylene because of the ethanol was suddenly become very much available. To summarize, so for all 20 basic chemicals, if I could summarize the findings from BREW, we looked at two scenarios. At that time, we called that today and the future. So we looked into what's the best available technology at that time and predicted, for example, yield increase based on theoretical max. What we found out, message number one, is for C6 sugar-based chemicals, the overall impact saving is, anyway, there is a very good saving potential. But for maize, from corn, is lower than the potential than from sugarcane. And this is also found out by many other independent studies later on. Whereas lignocellulosic, this is a non-food feedstock, it's somewhere in between, so around 50–60% saving potential in terms of primary non-renewable energy. If we compare this with some other studies published about starch polymers, which is today one of the most important bioplastics ingredients, so there is no conversion of sugar in starch polymer. We use the structure of starch. We use the structure nature provided to us, trying to make a blend, modify it in a way that we could use as plastics. So starch polymers somewhere in the range like lignocellulosics, the saving potential. And the same holds for cellulose fiber. So these are not cotton, hemp, these are man-made cellulose fiber. They are chemical conversion steps behind to modify the degree of polymerization and among many other properties. So this was found at that time. We published some 10 years ago. And the question is, where do we stand today? So the POA, so lactic acid, was one of the 20 basic chemicals we investigated at that time. And today becomes a very important commercialized ingredient for bio-based plastics. So in 2007, the POA industry published POA made from cornstarch. This is a corn from US, from one of the highest yield state in the US. Also, another Dutch producer, they published a study on POA made from sugarcane from Corbion, and this is a simulation-based result, so it's not a real operation. What we saw is, compared to their petrochemical counterpart, which is what they aim to replace, that's polyethylene terephthalic acid, so PET, the bottles outside. POA at that time already offered 37% greenhouse gas reduction on a per kilogram polymer basis, not really a per real functional unit. After 10 years, what we notice is the petrochemical industry also have improved their greenhouse gas profile. So Plastics Europe published recently the new PET data, which is slightly lower because of different hydrogen integration. What I understand, they also changed allocation approach one way or another, not fully transparent to me. But however, let's say we trust their data for now. And look at the PLA has been also improving over the years because they did a lot of effort in process optimization, for large operation, commercial operation, more heat integration as such. What we will also expect for many other bio-based chemicals. Then we saw that for both petrochemical polymer and bio-based, the PLA, if we compare them, PLA still offer quite large. So the decreasing of greenhouse gas emissions from cradle to factory gate for the bio-based for PLA is faster than for the petrochemical. This gives sort of a bit hope, right? So we thought that was the conclusion from BREW. Still, many of the conclusions still hold true today. This kind of study was never, I don't see them a lot, so I thought it was kind of unique to share and still sometimes still look back to the conclusions and data method that we adopted in the BREW project. The next project I want to share is the PRO-BIP study. So this is one of my first work when I started my PhD, and this paper apparently is the most cited paper of all my academic career. I always laugh at this is the least academic paper I've ever written, and it's most read. So here, at that time we thought, there's a seems like a booming investment for the bioplastics. But what are the bioplastics? What kind of polymer are there? Who is producing those? And who has the ambition to expand their production capacity? And what kind of petrochemical polymer they can basically replace? So we also look into technical substitution potential. We look at indicators like market projection. So it's pure journalism of half a year and year. I wrote that paper. It's funny. It's not too academic, I would say. So this was one of the first paper. The question is first, can bioplastics provide a solution? What are we replacing, right? And the first question is, what is bioplastics? What is it? I started with a very fuzzy definition. 10 years ago, it was already fuzzy, and today remains fuzzy. There are two dimensions we talk about. We talk about biobased, which means that anything from biogenic resources. And we also talk about biodegradable. I'm going to twist your mind now. Biobased doesn't have to be biodegradable. And biodegradable doesn't have to be biobased. Are you still with me at almost 6 o'clock? So to simplify the whole thing, let's assume that the biodegradable has two dimensions. We say, yes, it's biodegradable by certification, whatever, definition, or no, it's not biodegradable. But it means, strictly speaking, given the time frame, you can have a different degree of biodegradability or not. Let's keep it simple here, yes and no. Whereas for bio-based, we can have 3 categories. Either it's not biodegradable, or it's fully 100%, or we have also something in between. It's partially bio-based. The commercial product you can find in the market, these are starch plastics. Usually it's thermoplastic starch blended with a biodegradable, but the fossil fuel origin polymer to make it. A lot of them are used in the agriculture sector and also for carrying bags. And the PLA, we just saw the impact. Polylactic acid, you see them a lot as in the cutlery, and you saw the cups outside for the coffee, the transparent single-use cup. Those are made from PLA. Next coffee break or end of the session, you go outside, you have a look. There's a triangle, has a resin number 7 and says PLA under it. So it's made from bio-based resources. And then we have bio-based PE and PP, which is chemically identical with petrochemical polyolefins, even polyamides, polyurethane, and with based on ferronic chemistries, etc. So these categories, so these are fully bio-based, but not biodegradable, because basically it's the same as, identical as petrochemical PE and polyolefin. And we've seen commercial products, very unique, Lego, the trees, the little trees, these are made from bio-based PE these days, high density polyethylene. So I always want to look, twice and 3 times. I have 2 kids at home, but these are always in their treasure box that I'm not allowed to touch, which is a funny concept. If we think about, Laurie also presented this biogenic carbon in technosphere as long as possible, right? If you think about the Lego, nobody throw away Lego, right? It stays forever. Forever, if I don't want it, I will sell it, but I will not throw it away. And just to think about from product design point of view, how to achieve that. And then we have partially bio-based product like the plant bottle, which contains about 20 to 30% bio-based content, because the ethylene glycol part of the PET can be obtained from bioethanol. And then we have a category which is biodegradable, but it's fossil fuel based. So these are a range of synthetic polymers designed to biodegrade, but they are from fossil fuel bases. So the carbons are fossil carbon. And then we have a category of traditional, let's say conventional plastic that is not bio-based and also not biodegradable. So except for this corner, everything else is called bioplastics. It's confusing, right? It's extremely confusing. And then the question is bioplastic good or bad? Oh my God, I cannot answer that. So going back to the PRO-BIP. The PRO-BIP study, so as I said, I did some journalism work. We did some projection, also collected data for the real production capacity that is installed. Before 2007, there were just 2 big players. These are the starch plastics and the polylactic acid. It's very, very small. It's in total, it's less than 0.5 million tons per year capacity. And at that time, we projected that the 3rd one is going to kick in very, very soon. That's bio-based ethylene, or based on bioethanol, and also bio-based polyolefin will be developed there. And we also projected, by the time, 2013, a 4th one will kick in, a big one, which is PHA. And this trend will grow, endless grow. The reality is, no, it's booming. The industry is very dynamic, but it's not as optimistic as I was 10 years ago. In 2018, the Nova Institute published the real capacity in that year, for that year. So the real capacity is about 2.1 million tons. So it's 2 years away from 2020. What is happening is, so the growth of POA, growth of starch, was evident. So that was observed. This one didn't happen. PHA didn't happen. So it's by far, this is nothing like 1 million ton, nothing. It's about a few thousand tons worldwide, really at the pilot scale. It's no commercial large production. So it means also this innovation path, it's not that easy. There are issues with PHA. There are various issues. The barriers are not, I'm not going to go very broad here, but we could see that this is an industry still in a trial and error phase. Not that straightforward. Good. And the 3rd case I want to share with you is the recycling. I've done some work on PET recycling under the request of actually industry raised that question. So this is a textile, or say consumer product industry. They use a lot of PET fiber. They ask a question: can you tell me, is there a really benefit if I want to use recycled PET fiber compared to buying a virgin fiber? Can you tell me if I use bio-based PET fiber, which is already available in the market, compared to recycled, compared to virgin PET fiber? Can you tell me if I use recycled bio-based PET? All these options are on the table. So what we did is, first we're looking to the recycling technology and how do we achieve that from thermodynamics chemistry point of view. So we could do mechanical recycling, basically melt the polymer down and extrude it in the fiber again. Or we do semi-mechanical recycling where most part of it is still mechanical, but you do need to extend the polymer chain to a small level. It's a still catalytical process, or you could do a full chemical recycling. Basically, we're trying to obtain the monomers of PET and re-polymerize it. The third one apparently is very demanding in terms of energy, and sounded very demanding. So the first two has been implemented on the large scale, commercial scale. It's done today. The third one is, I don't know any of the company actually operating that with economic feasibility with the chemical recycling, but research, a lot of research has been ongoing. We also tried a different allocation. As we know, bottle is a waste. The bottle is not a waste. It's a secondary raw material. I will not go very deep here. If we are interested, we can discuss different in the LCA perspective. So we compared recycled PET, we compared bio-based PET, and we compared recycled bio-based PET. What we have found, this is one of the graphs I want to show. The reference system here refer to virgin PET. And we know the system goes like this. First we make bottles, because bottle is the most, the value is the highest. Also the polymer itself has higher crystallinity that you can basically recycle into fiber, which you only need an amorphous phase of the polymer. So we first make a bottle, recycle into fiber, and let's assume a fiber cannot be recycled any further. We burn it with energy recovery. So this system delivers bottles and fibers, and of course the energy recovered from waste incineration. The reference system, so what I did here is called system expansion by enlargement. So it's not system expansion by substitution, but enlargement. So the reference, the reference here, system here contains the impact of producing the same quantity of virgin PET bottle, and we don't do recycling at all. This bottle will be used and burned. And then the impact consists of making virgin PET fiber, and we don't recycle it, we burn it. And burning PET also emits greenhouse gas emissions. So this is our baseline to compare. The recycling system, we call that the baseline recycling system here. We have virgin PET bottle produced, and we have some effort of recycling. We need heat and electricity and energy input, and there's emission also from the recycling process. And then we make virgin PET fiber, extruded into fiber. And then the recycled PET from bottle and fiber here. So the red part is the recycled PET for both bottle and fiber. Oh, this is still virgin PET. So these are recycled PET bottle, recycled PET and bottle and fiber. So at the end, all the total amount of fiber cannot be further recycled, will be incinerated. The carbon is released again in atmosphere. And then we look at the same way, we look at virgin bio-based PET, actually it's partially bio-based PET, and recycled bio-based PET systems. And if you see if we can keep the carbon in the bottle and the fiber, as long as possible, we can avoid some waste management. We only do once waste management, not all the time. And we could reduce the greenhouse gas emission by at least, in this case, 1/3. So there is a proportion between bottle and fiber, depends on the market demand. In this case, about 30% of the PET granulate is going to the market of bottle, and another 70% goes to the fiber. That's why the bottle has lower impact than fiber. Good. Yes, what I want to share this is a fuzzy graph. Here we have we put a range of products in comparison, a range of forms of material. So the circles are polymers, so really at the polymer level. The square, the orange ones, these are fibers, and the triangles, these are bottles. So in general, bottles are more energy intensive than fibers, and then polymer is the basic form. What we saw is the general trend is the bio-based or recycled bio-based decreases, and then we compare with viscose, tensile, and modal, which are the 3 types of man-made cellulose fiber. It's a very large range overall. We try to figure out where does the bio-based material stand compared to their petrochemical counterparts. Why do I want to do this? First, because I can. Second, as I said, the study was commissioned by a textile company, by a final consumer goods company. They like to know what are the options for them, because PLA is also used for textile fiber extrusion, the same for the cellulose fiber. So as personal guidance, I'm a woman, I go shopping. When I look at the clothes I want to buy, I always flip around to see what kind of material is it, and I take that as my guidance. It's my personal thing. Just kidding. So not only for a large cooperative, I could also make something for myself. The last study I want to show you is the BIOSPRI project, which is recently finalized. So I'm not the only person asking this question, whether there is environmental benefit of bio-based plastics or not. The European Commission asked that too. So we were asked to conduct 7 LCAs for 7 commercialized bio-based products. These are very common products, from PET bottle, from horticultural clips and binders, drinking cups like the one we use outside, carrier bags, food packaging film, single-use cutlery, agricultural mulch film. So these are the products we found commercially available on a large scale. Okay, I will be fast. The unique part of this project is we know that for many LCAs, as we see here, many LCA, they don't include all environmental impact categories. So we looked into past 10, 20 years. Most LCAs publish results on climate change. Majority of them also look at energy. Some of them look at important category for bio-based product like eutrophication and acidification, whereas for land and water, it's very minimal, the reported LCA data. So in BIOSPRI, we try to look into all together, so 16 environmental impact categories that are defined by the PEFCR. Then what did we find out? Okay, how to read that? So these are the green part. So these are the single score, the final score of all 16. The green part is the environmental impact from biomass production, including land use changes. The brown part is the polymer and material conversion, and the blue part is the plastic conversion, so from polymer to plastic final products, and transportation and end of life. What we found out is, seems like the biomass production phase is not that substantial for many of the 7 products, except for except for beverage bottles, where sugarcane is there as a feedstock. And the high impact of sugarcane from bioethanol is because the sugarcane harvest in Brazil still has the old practice of burning sugarcane in open air that creates particulate matter as such. But this will also change very soon in the future. And then we have different end-of-life scenarios, which leads to different type of interpretation of the result. And one of the key conclusions, what we found out, is the food residue that you assume in end-of-life scenario has a very high, very strong impact for greenhouse gas emissions. So to summarize, if you remember the whale picture I showed earlier, I didn't really expand that. I was thinking, what is elephant in the room? Where is the whale in the room? We all know material, energy consumption, and climate change are closely connected. We've done enough LCA at this stage to understand the impact of the entire chain. What we didn't really understand, I think, do we understand the complexity of the land? It's not fully explored for bio-based material. So we heard a lot today, we need to obtain energy, food, feed, material, everything from the land. Do we understand the complexity behind? And we also don't know the end of life. We don't know very clear where this will end. On top of that, we heard a lot about today, degrowth, the term. So if we increase the ratio of recycling, reuse, reduce actually, how this whole picture will look like. My last request, I know I will get a question, but before that, I first ask you a question. Here is a PLA cup. Polylactic acid, by certificate, is biodegradable. And imagine you are going to Netherlands visiting me, and we have a 3 waste management system that you possibly to consider to dispose of this cup. So we have this organic waste bin, we have orange bin, which is for plastic waste, and we have the rest that you throw everything goes into incineration. And there's a 4th bin of paper. I trust people are decent. Don't throw something like this in the paper. Which bin you are going to throw this cup? This is not a scientific question. How many of you will say composting? Oh, 1, 2, 3. How many of you will say plastics recycling? Comparable. How many of you will actually put it in a gray bin, go to incineration? Oh, great. So why do you put it in incineration? Because you don't know. Because you don't know that's biodegradable, because it looks like plastic, feels like plastic. But if I tell you that's by certificate, biodegradable, maybe I should put a logo there. It's confusing, right? It's very confusing. I tell you, it's by definition biodegradable, but it will not degrade in an industrialized composting site because it takes too long to decompose. The industrialized decompose system takes like 2 weeks every batch, 2-3 weeks a batch. This cup will not degrade in 2 or 3 weeks. So it doesn't work in our current waste management system. And if you throw it in the orange bin for plastic recycling with all the goodwill, you mess up the plastic recycling system because the glass transition temperature is so low for PLA. It will jam. It looks perfect like PET. It will jam everything, jam the machine. So in the end, maybe it will be just shredded, compressed, and sent to the incineration. And then we think about what is all this about? I think, what is all this about? It's innovation, all this effort, decades of effort to bring PLA to our daily life. What is the responsible innovation? What is missing? System thinking is missing. Thank you.